Okay. 1, 2, 3. Yes, we are online now. Okay. Great. We are live now. I'm not sure whether, I think for some reason I'm not. Kelly, can you talk whether, I want to see whether I can see you.
Oh, yeah, sure. It's good to be back here.
Funny enough, I don't see you on the actual stream of,
That's strange. Really strange.
It keeps switching between you and me. Not in one sort of in one screen like before. And maybe I should turn you. Guys, thank you so much for being patient. I swear to God, like you wouldn't believe everything broke today. Everything, down to everything. I mean, okay, maybe it's going to be on view. Oh, okay, good. I think now it's going to look on. All right. Okay, good. Now it works. Now it works. Okay, so let's get started. Guys, first of all, thank you so much for being patient, and apologies for massive delay, like 25 minutes. You wouldn't believe that we were working really hard in the back to fix the problems, because the mic broke, the screen broke, the connection broke, my laptop just stopped working. So I had to bring another laptop. Like everything that you could imagine went wrong. So hopefully, fingers crossed, this is not the sign of things to come right now, okay? Anyway, again, we're back with you guys. So today is going to be all about autoencoders. And once again, Khalid is here. Really good to have you, Khalid.
It does feel good to be back and to be live. We started very early, 15 minutes prior to this, all that could go wrong went wrong. So definitely, it's good to kind of have redundancy. It's good to look into this going forward. But thank you for your patience. And Mehran has something special. So Mehran, continue going.
All right. Okay. So yeah. So in the previous video, we looked at the Celeb A data set. We looked at the images. We did some cool visualizations. The code has been pushed to the GitHub repo. So you can look at the Jupyter Notebook. You can play with it if you want. But mind you, you have to download the data set on your local machine, okay? That's the only thing you need to take care of. Now, as promised, today we're gonna talk about autoencoders, and it's gonna be mostly sort of a broad, let's put it this way, a broad view in terms of what autoencoders are, why do we use them, and maybe also like what are the most common types of autoencoders. And then of all of those types, we will be in this series, we will be focusing on variational autoencoders. Okay, so I'm just going to share my screen. And Khalid, at any point, if you had any questions, just give me a shout.
Absolutely.
Yeah, and you can see that I've changed my laptop, because I used to have a scary sort of image of myself, like a Terminator, and now it's a different screen, this sophisticated blue thing, whatever it is. So I brought my pad with me, and one other thing that broke today, even though this pad was charged, right? Even now it says low battery. Everything. But it's connected now, and hopefully it can work at the same time as it's being charged. And if not, oh yeah, it can. Okay, good. One thing is working. So yeah, guys, before we get started, I just want to say that most of these slides have been inspired by Ahlad Kumar. His presentations on variational autoencoders were amazing. His channel, again, with the same name, Ahlat Kumar, is available on YouTube. I watch his videos. The guy is amazing, so do check him out. And Ahlat, if you're watching, thank you very much for amazing slides. I borrowed a few pictures from your slides. So let's talk about autoencoders. So this right here is a shape of an autoencoder, which is an artificial neural network, right? So if you look at here, we've got an input data, X, coming into this artificial neural network. So you can maybe think of, let me pick a pen here. So this chunk, right? This is the autoencoder altogether, right? So the input data comes in, which is this guy, comes in, and something happens in between, right, in the autoencoder, and some output will be put out, right? But what is happening inside this autoencoder? Mind you, an autoencoder, there's a reason why it's called an autoencoder, because it grabs this input data and through multiple hidden layers here, it sort of compresses the dimensionality of your input data to a much smaller dimensionality called Z. We also call this hidden, this sort of representation, maybe this layer in the middle of your autoencoder, we call that a bottleneck, because that is what it is. It's a bottleneck. And it has generally a much lower dimensionality compared to the original input data. For example, if you have an image data of digit 4, it is, say, let's say maybe 100 by 100 pixel image, which is basically the 10,000 scalar values. Your Z vector might be of the dimensionality of 100, right? So there is a massive dimensionality reduction happening. And then, yeah, Khalid?
So yeah, I'm a little confused already. So get used to me interrupting and asking questions. So when you say input data in this case, you mean something like a single image, or is it the entire image set of images we have in the collection?
Okay, so at every point we consider one input data right now. It's a simple example here, but can we mean multiple images when we talk about an input data? Of course we can. So it all depends on how we treat this, but just to keep this simple at the moment, I'm just gonna say that, okay, one input data comes in, like one image, one signal of a sensory input, like one number, one vector of values, just one input data comes in, and something is, I'm gonna say what that something is. Something will be the output of the network.
Okay, a follow-up question. So when you say compression, now I'm looking at the green sort of half triangle, the encoder bit in there. When you say compression, I know from the last session we had, a single image would have 3 channels. So there were 3 channels. And if we think about it in form of like a matrix or whatever, then we can think of it as 3 different layers or 3 different matrices. When you say compress, how different is it from just kind of squeezing them into a single channel or layer? What do you mean by compress?
What I mean by compress is that, so I don't mean that you're gonna reduce the number of channels. I mean that each channel will be compressed into a much smaller sort of vector. Let me put it this way, right? So okay. you could look at it in a different way, like 3-channel image comes in, still only one vector of values would be the compressed version. So there is no sort of necessary correspondence between the number of channels in an input image and the dimensionality of the compressed vector. This Z is just a compressed vector. I mean, it's literally a bunch of, like, maybe you can look at it just as a vector of values, but the input could be a beautiful image, colorful, like 3 channels, like it could look really fancy, but this would look like an ugly vector, for example.
Right. Okay, cool. Okay.
Okay.
Yeah.
So the first half of this autoencoder, which is this chunk, right? This is the encoder part of the autoencoder. That the job of an encoder is to compress the input data into a much smaller dimensionality, right? And then we have a second part of the autoencoder, which is called the decoder, which is this guy. And when I say decoder, it's just a bunch of hidden layers with weights in between them. It's just a fancy way of saying we have hidden layers here, or we have layers of an artificial neural network here. Their job, the job of this entire decoder, is to bring Z into the original dimensionality of the input data. So if the original input data was, say, 28 by 28 pixels, which is a 28 by 28 matrix, this ultimate output that comes out of this decoder would have the exact, and I mean exact, dimensionality of the input data. Right? So we compress into a lower dimensionality, and then we decompress from the compressed version. And the goal is, you might wonder, why the hell are we doing this? The goal is that when we have an input image that, if you think about, for example, an image, you have raw pixel values. There is no meaningful features out of this. Like, it's the raw data without any meaningful features. And we are giving this to an autoencoder, and we want the network to be able to compress it into a meaningful vector that is hopefully more informative about the content of that image than the individual pixel values of an input image. And then if it can decompress it, and if it could make this output image a replica of the input image X, meaning that it can encode and decode the original image, and make this guy, this output, as similar as possible to the original input, then it is auto-encoding the input data. Let's say the network learned to do this really, really beautifully. Then why are we even using this? Like we already have a data. Why are we making a copy of it? Like, why? Right? The first time I learned about autoencoders, that part was really crazy to me. Like, why are we even bothering with this? The reason is that if the network learns to compress and then decompress, then the hidden representation at this bottleneck, this part, it is volume-wise a much smaller representation of a much bigger input data, and yet you can say that there is something very interesting about this hidden representation, about this bottleneck representation, meaning that it contains meaningful patterns and features in a very concise and summarized way about a much bigger input data that has only raw values. In other words, once you create an autoencoder like this, right? Let me erase the mess. Can I just erase that thing? Okay, so this means that if you have an autoencoder that learns to, let's say, exactly replicate the input data, this means that you have a smart compressor, basically. And what you can do is you can actually get rid of the decoder part, right? And just keep the encoder part. Yeah? And just keep the left-hand side. Just keep this chunk. Keep this. And get rid of the decoder. What this means is now you have a smart translator that if you have millions of images, right, that this autoencoder has learned to replicate, then it means that if you want to do, say, classification on those images, if you want to do regression on those images, if you want to do whatever with those images, you can put all of those images into this encoder part, convert them into a much more much smaller, much more informative, and much more efficient in terms of size, convert them into a very small embedding. Each image would turn into a much smaller vector, and do whatever you want on those smaller and hidden representations, rather than doing them on the original input images. And experiments that we have in machine learning have shown that if you work with the bottleneck representations, chances are your experiments will be your let's say whatever algorithm, let's say you want to use like k-nearest neighbor classifier on the hidden representations of the images, learned from an autoencoder, versus if you were to use KNN maybe on the actual raw images. Experiments and the literature has shown us that working with these bottleneck representations has shown a lot of improvement, let's say, on the performance of your machine learning algorithms. So this is one of the main reasons they use autoencoders, simply to learn how to properly compress something. Yes, go ahead, Sally.
Am I right to assume that what the bottleneck does is it gets rid of all the fluff in the original input? So essentially, a default representation might have a lot of redundancies in it. And then once we pass it through the encoder, and of course through the decoder eventually, and we get a perfect alignment between the reconstruction and the input, the bottleneck will contain a zero fluff representation of the input.
Yeah, exactly. That's exactly right. And it learns what to get rid of. Like, for example, Matthias in the chat box has a comment here. So he says that the way the bottleneck has condensed information reminds me of how a CNN would get image features, for instance, right? Like, for example, he's also asking, what is the main difference between autoencoder and a CNN in this regard? That's a very good question, and that connects with what Khalil just mentioned. The network is basically learning to get rid of what is redundant and also focus on what is relevant. But it learns how to compress to a much more informative set of vector values that say something about those images that the raw pixel values might not say that. For example, you and I, when we look at images of cats, probably all we care about is 2 pointy ears, vertical pupils, and maybe some whiskers and some sort of a tail. We don't look at the sunshine. We don't look at the color of the grass. We don't look at the brightness of like the shadow here or there. We compress it into just meaningful features. And that's it. That means we're looking at a cat. Now, CNNs, they learn, is very similar in some sense. CNNs learn what to filter. Each filter in a convolutional layer is something that we try to learn when we train a convolutional neural network. Each filter keeps changing until it learns the patterns to which it has to be sensitive. For example, if you and I were going to artificially create filters for an image, we might say, okay, of course, horizontal edges are important, crooked edges are important, vertical edges are important. So these are filters that you and I as humans are creating. A CNN learns the filters itself, right? That's a big difference. So it learns what to look for. Now CNN, an autoencoder learns how to compress to a meaningful representation that says something about that image that the raw pixels might not say necessarily. Okay, and also also like to add that you can combine CNNs with autoencoders, right? You can have convolutional autoencoders. So instead of the autoencoder learning how to compress raw pixel values into the bottleneck, it learns how to put this, like it learns filters that can extract patterns from the data, which can be efficiently compressed into a lower dimension that is the bottleneck. So it combines pattern recognition with the compression ability. You know what I mean? It becomes a different monster. You can add, on top of that, you could add LSTM connections, like with loops. So all of a sudden, you have an autoencoder that learns filters on a spatial sort of pixel space, meaningful filters, as well as would learn temporal dependency between in your input data. Let's say it's a time series data. And it also learns, because it's an autoencoder, it learns how to compress temporal and spatial patterns into a lower dimensionality that is your bottleneck, and then decompress it, if that makes sense.
Yeah. Is it one last question?
No,
is it
great.
right also, like, so I'm trying to draw analogies with processes that I'm familiar with, and my question here is it right to think of the encoder as a feature extraction and selection process? Because what we end up with is a new representation which likely contains latent features that aren't, you know, if you look at with the examples of the cat you talked about, maybe I'll be focused on the whiskers and the ears and the eyes, but the eyes might be not a very important feature to the machine or to whatever algorithm we intend to use downstream. So is it right to think of the encoding as a feature extraction and a selection process?
Exactly. That's exactly what it is. It extracts through compression. Now we have other sort of autoencoders which they don't compress, they actually expand. it expands to a higher dimension and then de-expands to the original dimension. They're called over-complete autoencoders. They're very interesting because I mean, I don't want to go into the detail of that, but maybe at the end of today's video, I'll talk about it. You can remind me hopefully if you remember, you can remind me of that, but it's a particular type of autoencoder that has some interesting abilities. But
I'll keep that in mind.
Hopefully you won't forget. And guys, hopefully you can remind me at the end of the session. Good, Matthias. I'm happy you liked the explanation. Good. So yeah, and if you notice, I'm looking at the encoder and we have this sort of G phi as the notation. And for decoder, we have F theta. The reason is that you can think about encoder that are the layers of your neural network, because those layers have weights. So those weights are your learnable parameters. If there were convolutional neural nets, they had filters that then those filters would become the parameters of your encoder. If you had LSTMs, again, the parameters of an LSTM would become the parameters of your encoder. So this phi simply refers to the learnable parameters of your encoder, and G is your encoder. It just means we have layers that have parameters to be learned, basically. And here the same story. Decoder is again a bunch of layers which have weights. The decoder is denoted as F, and the parameters are shown as theta. Okay. And yeah, so X comes in, X prime comes out, and ideally they are the same. Ideally, they'll be very, very close to each other. Okay, so that they can reconstruct it beautifully. The loss, I wonder, like I don't want to get into it, okay? Hey Gunjan, welcome. I don't want to get into like too much detail, but let me ask Khalil this question. Khalil, would you know, like, if the goal is to reconstruct the input data, can you define with that, like in simple terms, how should we define the error, the loss, like how bad we have done?
So I suppose something like a mean squared error might come in handy because, you know, it's numbers, and what we're trying to do is reduce the difference in the numbers. So some sort of squared error or squared loss will work quite well there.
And when you say squared error, error between what and what?
So error between the input and the output. So if, yeah, that's my thinking.
Exactly, well done. The input and the output is basically the reconstruction of the input. It means how well have I been able to reconstruct this bloody X? That's what it is, right? and mathematically speaking, this is a formula. It might look really, depending on where you are in your machine learning journey, it might look like, what the hell is this? But I'm gonna break this down with you with a simple numeric example, okay? But loss or error, as you notice, I'm sort of denoting it with two parameters. One is phi, one is theta. Why? Okay. By the way, Khalil, would you know why I'm defining it as a function of phi and theta?
I could take a guess. I don't know, but my guess would be that the data has been transformed. So essentially, G would be a function of the input weights or the input itself. This is phi at that particular stage, while theta would be derived from the bottleneck. So that's a representation from the bottleneck. So somewhere around there, I'm not sure if it's the actual values or the weights, but I would lean more towards the weights. So it's just kind of the change in the weights across the network.
Okay, that was close. Or maybe you said exactly what I'm about to say. Now let's see if there's a gap. If I'm going to reconstruct what you said properly, basically, pun intended. The thing is, I'm going to measure the difference between reconstruction and the input data, right? The reconstruction X prime is the output of my network, right? So the output of my network, how have I been able to generate that output? Through G of phi and F of phi and F of theta. So all those weights got, multiplied together, summed up together, nonlinear, blah, 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 until that poor X turned into X prime, right? So that X prime, if you want to mathematically describe it, is a function of F of theta and G of phi. And F of theta is a function of theta, the weights in the decoder, and G of phi is a function of phi, that are the weights in the encoder. So that is why the loss is the difference between X prime and X. And because X prime is a function of phi and theta, so the loss is a function of phi and theta. The loss always is a function of your learnable parameters. Always. If it's going to depend on your output in your neural network, it will always depend on your parameters. That's why in backpropagation, you always take the gradient of your error with respect to the parameters, because it is a function of the parameters. Otherwise, you won't be able to take the derivative with respect to, with respect to your parameters and get a meaningful value. If it was independent, you would always get 0 for all the gradients because they're independent. Yeah. Now, mathematically speaking, what Khalil just described in terms of the difference or the mean squared error can be described as this. So ignore 1 over n, sigma 1 to n. Ignore that for a second. The ith image, let's say X is an image. The ith image comes in. This is the input. Right? This is the same guy. This guy comes in. That poor guy, which is the same guy again here, would go through G of phi. So when this happens, when G of phi happens, this X is now here has traveled through G of phi. And then on the output of G of phi, which is Z, F of theta is sort of applied. So F of theta of that. When that happens, we get X prime. So this would be the output, immediate output out of all of that. So in other words, I get the X of I, or the ith input image, let's say, or input data. I encode it into my bottleneck. Then I decode from that bottleneck. And I get X prime. So effectively, I mean, then we put I here for consistency, the ith reconstruction image. So I'm effectively getting X, the ith X minus the ith X prime, which is the reconstruction of that. Subtract these two from each other, square it. That would be the error for those two images, like the image and the reconstruction image. And the reason we have N here is because let's say you have 1,000 images. So you do this for 1,000 images. Then you get 1,000 values that you have to sum together, which is the sigma, and then you divide by the total number of images. So it would be the average squared error or the mean squared error, right? I get that this might be a little bit confusing if you're not familiar with autoencoders. So that is why I have a little surprise. I have a very simple, cool numeric example of exactly what happens to your data, right? So we've got the same image on the top. It's the same image. We have the loss function that I just described on the right-hand side. Imagine in our data set, we have two input vectors. So they're not images, they're two input vectors. The size is 3. And we want to compress it to the size of 1, and then we want to decompress it to the original size of 3. In other words, we would like, I may change color maybe to orange. In other words, when the first input data comes in, which is x1, then the input to the autoencoder is going to be 1, 2, 3. This is the input data. This is your x, the first input data. Tell me something. According to this image, G of phi is happening here, right? Before we get to Z, that is here. Can you tell me what G of phi looks like? I keep saying it's a function of parameters phi, but if you want to like basically write it down, can you tell me, if I want to write it down, what G of phi would look like?
Would it be the dot products of the weights and the input? So exactly. 1 times 1 plus 2 times minus 1 plus 3 times 10.
Exactly. That's exactly what it is. So that's the functionality of it, right? So this is basically, let me reduce the size of this a little bit. So first of all, what is phi, by the way? If you want to denote what phi is exactly, what is it? The parameters.
Phi will be the vector W. So essentially the elements, the weights W1, W2, and W3.
Exactly. Well done. Right. So G would be W1 times the first element. So 1 times 1 plus W2 times the second element, which would be minus 1 times 2, plus W3 times the third element, which is 10 times 3. And by the way, why are we multiplying and summing? As Khalid said, it's a dot product operation, right? That's the typical way between fully connected layers. We always do a sort of dot product, start between the weights and the input data. Now, a quick calculation. What would be the output? 1 minus 2 plus 30. So 29. So the output of G of phi is 29. So if I want to fill this table here, G of W1, W2, W3, so W1 is going to be 1, W2 is going to be -1, W3 is going to be 10, right? And G of that, I don't want to make this messy, but G of that is going to be the dot product of this W vector with the X. The output of that is 29. So Z is 29, right? Now, we have Z as 29 here. Now we have encoded into a smaller dimensionality. Now we want to decode. How do we decode? Using our f of theta. So again, the theta is, again, the parameters of f, which is W4, W5, W6, similar to the encoder. And again, a dot product. Khalil, would you do me a calculator here? If you have a calculator. So -3 times 29 plus 10 times 29, which is 20. Oh, sorry. Actually, you don't need a calculator. Sorry, it's that's not how it's gonna happen. So the way this is gonna work, my bad. Sorry, guys. So -3 times 29. What's gonna happen? With the minus 90, 87, right?
-87. Yep.
Yeah. Sorry, I was gonna dot product, but it's like one element by one element. 10 times 29.
290.
2 times would be 58.
Yep.
So the elements of f are -3, 10, and 2. And x prime is -87, 290, Jesus, and 58. This is terrible, by the way. I hope you guys can realize why this is so terrible. Let me erase these. Can you tell me, Khalil, why is it so terrible?
It seems the difference between G of theta, G of phi, and f of theta is quite huge. So the loss will be massive. And what we're trying to do is to minimize that loss. So we're trying to make it as little as possible.
Exactly. So x prime, which is supposed to be a reconstruction of x. X is just 1, 2, 3, and reconstruction is -87, 290, and 58. Now, how can I use this formula to compute the loss? Remember, we have a sigma here, right? This sigma is for, you do this averaging, summing and dividing by the total number of examples. If once you want to average the results across your entire data set. Here we have 2, right? So I'm just gonna do this chunk for now, this first chunk. And then I'm gonna average the output of all of those together to get one loss for the entire batch of data that you have, right? So the loss here, can you tell me what that loss would look like based on this formula?
So that would be 1 minus -87.
So
that
1
would give you 88.
minus 87.
Okay. And squared, right?
Yes.
Okay. And then that'll be plus -1 minus 290. And
Plus?
then plus 10 minus 58.
Now, that's great. Well done. So just guys, mind you, this plus has nothing to do with this sigma. Okay? That sigma is summing across data, your input data. Like if you have 10 input data, you will have 10 summations. This sum is across the dimensionalities. dimensionality of your data. Because you get 3 values, 1, 2, 3, one for the first dimension of x prime, the second one is for the second dimension, third one for the third dimension. You must have a way, you must think of a way to aggregate these 3 values together to get into one scalar value that says, okay, this is how terrible you have done in reconstructing this one input data. So one way of doing it is to sum across the dimensions of your input data, okay? So let's say, I don't think we have a value for this, do we?
So that would be 7,744 plus. I need to compute that.
Don't bother.
Okay.
Let's assume a value. It doesn't matter. It doesn't contribute to note exactly, but I'm gonna put a big value. Let's say the output of that summation is 1,000. Right? We do a similar thing again, and a similar thing with the second data point. This time is 4, 5, 6, right? Again, we do the same, exact same thing, the same parameters, right? Let's say this time we get 2,000 as the error, right? Now that we have 2 loss values, one for x1, which is my first input data, the other one for x2. If you have 1,000 data, like input data in your data set, you will have 1,000 of such values, right? Now this chunk comes in, this averaging. You sum up all the loss values together. We have 1,000 plus 2,000. That's it? Yes, that's it, because we only have 2 data points, right? Sum them and divide by 1 over n, right? 1 over n. N is 2. So divided by 2. That would be 1,500. I want to be clear. This is the reconstruction error for reconstructing the first input data. This is the reconstruction error for reconstructing the second input data. This is the average reconstruction error across all of my data points in my data set. Does it make sense?
Crystal clear.
Good, good. Of course, there is a sort of minute detail here that you might think, okay, wait a second. I put in the first input data 1, 2, 3, and I reconstructed it really poorly, right? You would like that mean squared error to be around 0-ish. Then why do you go ahead and input the second input data now? Why don't you update the parameters of your network and then put in the second input data with the hopes of doing, God, please, doing better with the second input data? Would you have any answer for that, Khalid?
No, not really.
That's
I would
okay.
say it's possible that we're trying not to, if it might take much longer to get to a satisfactory solution if we're doing it on a sample by sample basis. It's probably better to get a view or to learn from the entire data set in a particular pass, and then eventually update the weights, because the weights reflect not just the representation of a single sample or image, but for the entire data set. That's
a lovely way to look at this. That's exactly true. I think the key part was it will take forever to get to a satisfactory solution, because if you're going to update the parameters with every input data that comes in, you're doing effectively stochastic gradient descent. If you're going to update the parameters after every mini batch of your data points, then you're doing mini batch gradient descent. If you're going to do across the entire data, you're doing full batch gradient descent, right? So the different styles would converge differently, okay? So that's very true. So I just kept the parameters fixed just for simplicity for our example. Now, before I move on, so this is, by the way, this is the vanilla autoencoder. If you understand this properly, you have a solid foundation to understand, and I mean any other autoencoder. Okay, so you already have a very strong tool in your arsenal. I want to just tell you something very important that would connect everything to the initial part of our talk today. Let's say for the first input data, we did a brilliant X prime where we had like 1.5 here, maybe 1.98 here, maybe exactly 3 here, meaning that X prime, look, it's very close to X, right? And let's say again for the second data vector, again, we did something very good, like let's say 4, 5.1, 6.02. Again, you see, they're very, very similar. Let's say the network has learned beautifully. It has kept changing the parameters of the encoder and the decoder across your entire data set to do this reconstruction really beautifully. If that happens, then what you can do, as I said in the previous section, the previous slide, you can get rid of the decoder and just keep the encoder, meaning that you can just keep G of phi, right? Then what you do is you grab your entire data and you pass it through your G of theta, and you get a much smaller in size transformed data set, meaning that if, for example, the Z representation for the first input data, let's say, okay, let's say you have 1, 2, 3, 4, 5, like each one of this is an input vector. Like each one of this is an input vector. Each one of them would be translated into a Z that is much smaller. Like each one of these guys would have dimensionality of 3, 3, 3, and you get a bunch of single values for each one of them. Now, this might not look that much of a difference in size, but trust me, if your input image is a size of 1,000 pixel values and your Z happens to be just like 5 values, then let's say if you have 100 images, each one 1,000 pixels, right? You would have 1, 2, 3, 4, 5, this many scalars in those images, right? But if you turn them, if you pass these guys into your G of phi and turn, not this guy. If you pass your images of 1,000 pixels through your G of theta and convert each one of them to a dimensionality of 10, with 100 transformed images, you only have to store 1,000 values. And it's, again, it's not just the quantity. It's also that this vector of size 10 happens to have a lot of very rich information about a pixel of size, an image of size 1,000 pixels. There's something about it, those values say something very profound about that, that input data. Why? Because your decoder f of theta, as you have seen, has been able to decode from that small representation the original image in a very beautiful way. So that means there's something very special about that vector representation. So you pass in your 100 images, you pass all of them through your G of phi, and you turn them into a bunch of small vectors. Now, this is your transform data set. You ignore your image data sets, you ignore your images, and use all of these small vectors to do whatever tasks you want to do. Do image classification, do like object detection, do whatever you want on those vectors, if that makes sense.
It does.
Okay, great.
It does. I can already see use cases, very interesting use cases. For example, in clustering, it's very common to have a data set with a large, cardinality. So you can imagine where if one had encoded vectors, then you'd end up with a lot of features to cluster on, and not all of those features are important. So one approach could be, do a little feature selection in here, and that could take a lot of time. Or you could just kind of train an autoencoder, use the encoder to extract the bottleneck, and then cluster based on that bottleneck. Now, whether it's going to get better clusters or not, I don't know, but it sounds like a good use case for that dimensionality reduction.
Yeah, absolutely, exactly. Mind you, if I keep, just before I switch to the next kind of autoencoder, this network is purely deterministic. And it's important to note that, because once we get into variational autoencoders, things will change big time. Okay. So if the same input is being put into the encoder 1,000 times, you will always get the same output. That's why it means it's deterministic. Okay. But yeah.
So when you say deterministic in this case, does the fact that these weights are randomly initialized, does it affect the type of representation we learn at the bottleneck? Or do you mean assuming the weights are the same? Yeah. The initial weights are the same, then the representation learned will likely be the same.
Yeah, exactly. Okay. So if the network is fully trained and you want to test it now, right? And you want to test it. Once the weights are fixed, the same input always results in the same output. That's why it's deterministic. But variational autoencoders are different. We're gonna get to it and why they're different and why we care about that. I'm gonna get to that part. Okay.
Okay.
And guys, before I switch to the next slide, please make sure that you will post in your questions in the chat box if you have any, and you would also join our Discord channel. I mean, we put in cool stuff, cool information here. So I've already, sent the link in the chat box. I'm just going to put it one more time and invite your friends to join. We want to hopefully make our network bigger on this. Okay. So the next kind of network, the next kind of autoencoder that I'd like to talk about is something that you might have heard about before. It's called a denoising autoencoder. This is the structure. Denoising autoencoder, right? Now, there is you probably have noticed immediately there's something different about this beast here. The only difference, is that in the previous case, you would put your actual X input data into the network and you would ask it to recreate or reconstruct your input data, right? Can you guess how that X will change here at the denoising autoencoder?
So the X would be further destroyed. I'm reading from the slide, so I must accept I'm cheating. But my thinking is this. My thinking is we already know that there are some redundant bits in X, which is the input. So in an image, it's very likely that some pixels are useless and don't contribute to an optimal representation. So what we're doing is we're adding more noise deliberately to it with the hope that what we learned is more optimal in the sense that it can handle variations in our input image. So essentially exposing it to, a larger or just a different set of representations that it could learn. So it's making it more robust, basically. Is that what it's doing? I'm thinking out loud here, so I could be wrong.
Actually, you used the exact, first of all, the ideas were correct, I think, and also the terminologies you used, they're actually like the exact terminologies spoken in the autoencoder sort of realm. You said robust.
Good to know.
That's the keyword, actually. If you notice here, your original input, this is your original input, right? This guy. You add some noise to different parts of it. Like imagine like this is your original digit number 4 image, and you're adding some salt and pepper noise to it. And then this becomes your destroyed input data. Or maybe destroyed is too dramatic, but let's say noisy input data. The rest is exactly the same as the previous slide. You still want to reconstruct, but reconstruct what? Would you want to reconstruct the destroyed input data? Or would you like to reconstruct the clean input data?
Obviously, the clean one. Everyone
Absolutely.
wants the clean one.
Absolutely. Like why would you not, right? Now, Khalil mentioned the word robust, and that's a key word. You see, reconstructing an actual clean image is easier than reconstructing an image that we have deliberately added noise to it. It's like we're making the job of the autoencoder even more difficult, right? Because we are making it more difficult for the autoencoder, the features learned, remember what I mean by features, the phi weights of the encoder and the theta weights of the decoder, you are forcing them to converge in values that are more robust to noisy images being the input to the autoencoder. They're strong enough to say that, okay, even if you have noise in your input data, we are so strong that we can still retrieve the original denoised image. That is why this is called the denoising autoencoder. So the features learned, the weights learned in a denoising autoencoder tends to be more robust to noisiness of the input data. For example, the sensory input, if you have sensors that are collecting information from the environment, those sensory inputs tend to be really, really noisy. And the sensory data is notorious for being noisy, right? So you can actually use the denoising autoencoder to sort of clean, let's say, your noisy input data. Funny enough, this is a minor digression. There are methods, there are autoencoding methods that believe me, you don't need the clean data to actually train the autoencoder to actually create, reconstruct the clean data.
Wow.
There's an amazing paper here. I read it like 6 years ago. Beautiful method. I mean, I swear to God, that was gorgeous. If I can find it, I'll post it on Discord. This is a brilliant method.
So this will be the second thing you've promised us on this stream. The first one being autoencoders that don't have bottlenecks. They have the reverse of a bottleneck. I'm not sure what that is called, but essentially
Expansion.
the middle layers are expanded. Okay, interesting. And then this one where we don't have clean inputs, but we're trying to reconstruct the clean inputs. This is something we should talk about. Yeah, I would love to know more about it.
Yeah. Yeah, could you just Khalil, maybe take notes of these points? Like, even if I couldn't cover it now, I can do it later, or maybe even put some information in the Discord.
Absolutely.
Thank you. Okay, so the loss function of a denoising autoencoder is exactly the same, except the input image has this little sort of tilde sign on the top of it, right? You see here. It just means that, look, the input data is not noisy, but we still want to reconstruct the original data. Okay, so the original clean data minus the reconstruction of the noisy data. Make this as small as possible. Hence, denoise the input data to the original data. That's the only difference. Everything else is the same. Okay. Now, I'm gonna give you a lot of fear right now. I'm going to instill a lot of fear in you, I think, in all of you, because I'm going to show you a very scary slide of variational autoencoders. Please don't get stressed out. Don't feel like you're not going to be able to do it. I will make sure that, listen, we will dissect it all the way, okay? So don't worry about it. Here it goes. Okay, this is called a variational autoencoder. There is something different about this beast. This is not a deterministic model. This can generate new data for you that doesn't exist in your training data or in your data set. It can generate new faces for you. That's one of the reasons we want to use this in this project, because we're going to be using the celeb A data set, right? Facial features, like faces of celebrities. We will be generating new celebrities for you, okay? And if you look at the entire mess here, a few things are different. Like, first of all, the encoder, like here used to be a fixed G of phi, but here we have a probabilistic encoder. It's not deterministic anymore. And the decoder used to be a fixed decoder, and that's it, a simple function. But here we have a probabilistic decoder. And whenever you talk about probabilistic whatever, you're talking about probability distributions. And when you're talking about if something has a probability distribution, it means it is a random variable. And if something is a random variable, it means every time you want to sample a value out of it, it will generate something new for you, right? And that is why the entire structure of a variational autoencoder is a generative model that is stochastic. Okay. Now, of course, I'm not going to go into variational autoencoder now. I just want to show you the big picture of how, like, give you some like basic terms as to what you will be hearing from now on about when we talk about variational autoencoders. But I will dissect it properly, okay? And you notice the loss looks really scary, right? I mean, still the goal is to reconstruct the input data. But just to sort of brush on the surface, we are sort of learning the parameters in the encoder, the probabilistic encoder. We are learning the parameters of a probability distribution, right? And from that probability distribution, we're going to be we will be sampling random values. With every sampled random value, which is again a compressed vector, with every sampled random vector, we pass it through another probabilistic, this time decoder, to generate a different input data every time, right? So that is the idea. It's all about sampling random bits. Because we sample different things, we will generate different things. Now, if you look at the loss function, you see this KL. Okay, what the hell is that? Like, what is a probabilistic encoder? Like, given input data, the probability of the sampled vector. What is this weird sign here? Like, what are we doing? What is KL of this distribution minus this? Like, what the hell is even this distribution? Like the probability of Z? You know, it's just weird. It's really scary.
So many questions, so many questions.
So many questions, exactly. And I just thought maybe it's a good idea to show you the kind of monster that we're going to be dealing with, okay? Just the big picture, very vague big picture. And we have expectation. E is expectation. Like, what is expectation? I mean, is it averaging, like across, like taking an average of a few values? But it's the expectation of a probability distribution, right? Where we have like this value here, which is like Z being sampled from another distribution. Like, it looks so complicated, right? It looks so weird. But trust me, the next session in our live stream, the goal is to derive this. Like we will derive this error function from scratch. Okay, and you'll understand what's happening in each part of this error function. What is KL? So this is KL divergence, a measure of difference between a measure of divergence between two distributions. What is P of theta? What is the Z given X? Well, what is all of that? Suffice it to say that the variational autoencoders, if you want to get ready for the next video, take a look at Bayes' rule. It has a lot to do with Bayes' rule. Okay? If you get comfortable with the ideas such as likelihood, prior distribution, posterior probability, if you get comfortable with these ideas, you will be really comfortable with the next video. Okay? So the goal of the next video, the next live stream session, is to derive this beast from scratch. That's it.
Sounds exciting.
Yeah. And it would be really interesting, like in terms of what we can achieve with variational autoencoders when we use celeb A data set, the celebrity faces. God, like guys, we've been talking about this for quite some time now. We have some interesting stuff for you, like with the variational autoencoder. You basically create new faces and you do things to those faces. I mean, there are ideas that you can do, like there are ideas that we have. Hopefully we'll be able to train our variational autoencoder in a proper way that loss would go very, very low, so that we could do very exciting, visibly exciting things to those faces. Like you could get Brad Pitt as an input and then like a Brad Pitt smiling as an input and then turn it into a frowny Brad Pitt all of a sudden. You can do crazy things, okay? All right, guys. So this was it. Just a sort of exploration of different types of autoencoders, the big picture. So we talked about autoencoders, vanilla ones. We talked about denoising autoencoders, and we talked about variational autoencoders. Now, the bit that I promised a few things. One of them is something that I can explain right now. But the paper that we talked about, I'm going to have to send an. I'll send the link to the paper in our Discord server. Okay, so I sent the link in the chat. So please do click and join the MLDAN server, so you'll be notified about all these exciting announcements. Now, the one thing that I can explain is the over-complete autoencoders, where the input data doesn't get compressed, but rather gets expanded into a higher dimensionality, and then again gets compressed into the original dimensionality. One of the reasons you give flexibility to the bottleneck, allow it to get larger, is that now the network has more ability in terms of, it has more of a leeway to play with your input data. If it has that ability, then it means that it might actually disentangle your input data into meaningful clusters of meanings. Let's put it this way. Like frequency information in one part, domain information in one part, extract different clusters of patterns into different parts of that larger dimension. Right? So you can think about disentangled representations. Right? Different features will be clustered into different parts of that large bottleneck. And then it will be decompressed again to reshape to reconstruct again the input image. Right? So it follows a different logic. It's not about compression anymore. It's about, disentangling the meanings and patterns into different clusters. Different parts of it might be useful for different tasks. Now, the goal is reconstruction, right? There is a very trivial solution for reconstruction if the input data comes in and it is allowed to be mapped into a larger dimensionality and then go back to the original dimensionality. If the goal is to produce the exact same input in the output, there is a very trivial solution here that the network might just say, I'm gonna do, can you guess what? Khalid? There's it doesn't need any genius like for the network to do this. It's very simple. Because the code layer is big enough, bigger than the input data, it can literally copy in the hidden layer because it can fit, and then copy it again in the output.
Oh.
So you just learn to copy. I mean, it wouldn't even bother with extracting representation. It just copies and then copies. And guess what? The error would be 0. Exactly 0. And you think, oh my God, I have a beautiful network. No, you don't have anything. I mean, the code layer. You haven't learned
anything. Yep.
Yeah, you haven't, right? So that is why the denoising part comes in. They actually add a little bit of noise in the input data, so that copying a direct copy of the noisy data would not result in the original data. It would result still in a noisy data. Thus, the loss will not be near 0. The loss would still be bad, right? So that is why if you add a little bit of noise and ask the network to still reconstruct the input data, it will not keep copying the noisy data because it's not a reconstruction anymore of the original data, right? So you can actually add denoising ability into overcomplete autoencoders to avoid this trivial solution. Yeah, but the paper, I'll send a link to the paper. Hopefully I'll find it. I read it like 5 years ago, but I'll send a link to the paper in our Discord channel. Any other questions, folks? Okay, if not, I think we have, I'm getting some messages in. Okay, so we have, looks like new members. Yeah, Matthias, I think you joined into our Discord channel. Welcome. That's great. Okay, Khalid, any questions?
None at all. Maybe for next session. I'm very excited about the variational aspect, especially sampling from probability distribution. So I suspect that in next session, we're just going to go deep to understand what precisely happens within that encoding phase and then also the decoding phase. So I'm going to save all my questions for that point in time.
Yeah, fair enough. Okay, guys, it was a pleasure. And yeah, I'll see you in the next one. Take care.
See ya.
All right.